We're off and rolling. Right triangle. Greek letters are usually used to represent the angles in a triangle. So we'll see the Greek letter and just the first few Greek letters. You don't have to go learn the Greek alphabet. We'll use alpha, beta, and gamma, Greek ABC essentially, to represent most angles in a triangle. And then sometimes we'll use theta. Those are the 4 Greek letters that we will see frequently. Alpha, beta, gamma. Alpha, beta, gamma, and then sometimes theta. Those are the 4 Greek letters that we use most frequently. When we look at a right triangle, we are dealing with a right angle and then 2 acute angles. Who remembers what an acute angle is? So an acute angle is an angle that has a measure between 0 and 90 degrees. So this is acute. And that means that alpha is less than 90 and greater than 0. So I'm focusing on that angle up there in the top left corner. When we label the sides of this triangle with these words, adjacent, opposite, hypotenuse, we're talking about those words in relation to the angle that we've identified, the acute angle that we've identified. So for that acute angle alpha, this is the adjacent side, this is the opposite side, and that's the hypotenuse. If we were looking at the angle down here, that would be different. For the angle in the lower right corner, this would be opposite, and this would be adjacent. Hypotenuse still is the same. Hypotenuse is always the longest side in a right triangle. And we define, the 6 trig functions. There are 6 of them. And the 6 trig functions are nothing more than ratios. 6 trig functions are ratios. So we look at the 3 numbers that correspond to side length, and there are 6 possible ways to combine those 3 numbers. There's 6 possible ratios. And this chart right here, this little table, we'll do it the same throughout the whole semester. We'll do sine, cosine, tangent on the left. So those are our 3 primary trig functions. And then the 3 trig functions on the right are the reciprocals of the ones on the left. And we'll do it in this order, sine, cosine, tangent, for a reason. We will see very shortly that tangent is sine divided by cosine. So putting it in this order helps you to take this, divide it by that, and get your tangent value. So if you close that door for me. Thank you. So that's the order, and if you just stick with that order, you'll be less likely to make mistakes as you move through the semester. So sine, cosine, tangent. And then over here on the right side, this top one is called cosecant. Cosecant is the reciprocal of sine. Reciprocal, remember, is where you take the numerator and move it to the denominator and vice versa. You flip it over. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. So here we go. So the definition of sine. So we're going to look at sine of this angle. S-I-N-E. Sine. And by definition, it's opposite over hypotenuse. That's the definition. And that's how we do things in math. We define some concept, make some definition, and then we move on from there. So we're going to do a whole bunch throughout the semester with these 6 trigonometric functions. But first we need to define what they mean. And this is what they mean. It's very simple. 6 trig functions, each one's a ratio. That's not too bad. That's not too crazy. Cosine, by definition, will be adjacent over hypotenuse. And right here this is the first nuance. You've got to remember which one is opposite over hypotenuse, which one's adjacent over hypotenuse. Just like when you were a kid trying to remember which hand was the left hand and which hand was the right hand. You've got to come up with a way to remember. The way I remember is that when I look at cosine, the word cosine, I think of this co, and I think of that as meaning next to. It's nearby, the pair. So that's how I remember it, that adjacent and co go together. I've heard other people say that they remember sine as opposite. They think of this abbreviation for sine, sin. They want to stay as far away from the sin as possible. And so opposite side is the furthest side away from the angle alpha. Whatever it takes, you got to come up with some way to remember. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Tangent is the opposite over adjacent. Another way to think of it is sine over cosine. Do you see that if we take the sine fraction and divide it by the cosine fraction, that we end up with opposite over adjacent? Do you see that? If you were going to divide those two fractions, you have a numerator fraction, and you're dividing it by a denominator fraction. And how do you do that? Take the denominator fraction, take the reciprocal, and then multiply across. So if you take this denominator fraction and you flip it, if you take its reciprocal, it's hypotenuse over adjacent, hypotenuse, hypotenuse cancel, and you get opposite over adjacent. What's that? Yes, exactly. Yep, that is the one. And now these ones on the right are easy as long as you've lined them up properly. Cosecant is the reciprocal of this. So that's hypotenuse over opposite. This is hypotenuse over adjacent. And this is adjacent over opposite. Typically, our procedure will be find sine, cosine, tangent, and then form the three reciprocals. If somebody asks me to find the secant of something, most people will tend not to memorize that this is hypotenuse over adjacent, but remember that secant is a reciprocal of cosine. Find the cosine ratio and then reciprocate it. And some of you who saw this in high school will be familiar with SOHCAHTOA. This is another way to remember it. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So that never worked well for me, but if that works well for you, use it. I can never remember how to spell SOHCAHTOA. So when I spell SOHCAHTOA, I'm actually doing this in my head first. I'm thinking, oh, sine is opposite over adjacent. So if it works for you, use it. Whatever works, use. All right, any questions on those basic definitions? These definitions will stay with us the entire semester. Oh, I still haven't taken roll. I'll do it right before break. I don't want to have it on the recording. That's no fun. Okay, we're now going to focus on a particular triangle. There are two special triangles that we're going to deal with a lot. The first is a 45, 45, 90 triangle. So we want to figure out the 6 trigonometric function values for 45 degrees. So, what is important is that the trigonometric function values for 45 degrees, they have to be the same no matter how big or small you draw your triangle. So if you've got your 45-degree angle and you make a huge triangle, as long as those angles are both 45, the trig function values are unique. You can't have one smaller 45, 45, 90 triangle have different trig function values than a large 45, 45, 90 triangle. So it doesn't matter what numbers I choose for the sides of this triangle. As long as I satisfy the Pythagorean Theorem, any number that I want to pick for that side right there will work. The simplest number to pick is probably 1. You want to pick pi? Pick pi. You want to pick 6? Pick 6. Doesn't matter. That side and this side have to be the same in length. They're both opposite a 45-degree angle, so those sides have to be equal. That determines the hypotenuse. We know the Pythagorean Theorem holds for every right triangle. So if we put in those two side lengths, 1 and 1, we see that the hypotenuse, whoops, that's 1 plus 1, that's 2. We see that the hypotenuse has length root 2. So we calculated that. And we are dealing with a physical quantity that is positive in measure, so you don't have to do the plus or minus square root of 2 thing. If you know that your outcome has to be positive, you don't need to put plus or minus square root of 2 and then cancel out the negative 1. It's understood from the context of the problem that we're just looking for positive answers. So negative square root of 2, even though it's a solution to this equation right here, it's not an option based on the physical description of the problem. So don't need to put it in there. Now, in general, if someone says solve c squared equals 2, obviously, you would have to say, okay, if I don't know the context, then c is plus or minus root 2. Right? Okay. So there is one set of side lengths for a 45, 45, 90 triangle. And again, it's not going to matter what side length you choose for that base and that height, as long as they're the same. It's not going to matter when we form our ratios. Okay, so let's come down here. Let's put these side lengths on. So we had a 1, square root of 2. This is obviously the right angle right there. And it doesn't matter. Both of these are 45 degrees in here. Let me focus on this one. Doesn't matter. Could focus on the upper one. So sine of 45 degrees. By definition, sine opposite over hypotenuse. That's 1 divided by square root of 2. And you all know how to rationalize a fraction. Rationalize the denominator of a fraction, I should say. How did I get from 1 over root 2 to root 2 over 2?
U times the top and bottom by square root of 2.
Mm-hmm. Exactly. So if you want to rationalize the denominator, you multiply numerator and denominator by whatever is in the square root. So 1 over square root of 2, multiply by 1. Right? Root 2 over root 2 is 1, so it doesn't change the value. And then root 2 times root 2 is 2. Correct. And my math lab will want its denominators rationalized. So make sure you do that. Now, let's do cosecant. That's the reciprocal of sine by definition. Which of these fractions is going to be easier? Which form of the value is easier to reciprocate and be done? The first one. So when you reciprocate that, you get root 2. And you're done. If you reciprocate this one, you have 2 over root 2. Then you've got to go through the rationalization process again, and you'll end up with root 2. Cosine of 45. Cosine of 45, by definition, we look at the angle. Cosine is the adjacent side over the hypotenuse. Same. 1 over root 2. Same rationalization of the denominator. Same secant value. Root 2. Tangent 45. We have two ways to do it. We can do sine over cosine or opposite over adjacent. So at 45, opposite side is 1, adjacent side is 1, 1 over 1 is 1. Or root 2 over 2 divided by root 2 over 2, that's 1. Or 1 over root 2 divided by 1 over root 2 is 1. Doesn't matter how you look at it. Tangent is 1. Cotangent is the reciprocal of that, which is 1. Reciprocal of 1 is 1. I want to point out one little geometric observation. Root 2 over 2, is that more than 1 in value, or is it less than 1 in value? Less than 1. Sine and cosine will all, especially when we're talking about acute angles, they can be negative once we start talking about some other situations. But sine and cosine's value will never be greater than 1. And when you're dealing with an acute angle, it will always be greater than 0 or less than 1 for an acute angle in a triangle. Look at it geometrically. You're taking this length and dividing it by that length. Hypotenuse is longer. So you're taking a short side over a longer side. So obviously that value must be fractional in nature. Right? Can't be equal to 1 or more. It's got to be less than 1. It's got to be fractional in nature. All right, so this is our first most important triangle. And you need to know these values. These here. These you will compute if you don't remember them. But these values for sine, cosine, and tangent of 45, those have to be auto. You got to be able to pick those out of your head really fast. Now we have a couple of weeks to get to the point where it's necessary to be that fast. And when we get to the unit circle, I'm going to have a nice visual way for you to remember that. Instead of randomly remembering sine of 45 is root 2 over 2, we'll have a nice picture, a very symmetric, geometric way that you can remember it pretty easily. But eventually you'll have to have those down pat. So the other two angles that we want to focus on come from the second special triangle, and it's a 30, 60, 90 triangle. We're going to have three angles that everything is built on, 30, 45, and 60. We're going to use the trig function values for those three angles pretty much every day of the trig semester. We will be dealing with those three angles. And again, when we get to the unit circle, there'll be a nice, easy visual way, and I'll give you a lot of tips on how you can get these values down pat. So, the same holds for this triangle. The values are unique. Doesn't matter how big or small the triangle is. If you have a 30, 60, 90 triangle, the trig function values that we find will be the trig function values that we find. We're going to take, in order to generate that triangle over there, we're going to imagine an equilateral triangle. Equilateral triangle has three sides that are the same length and three angles that are the same. So 60, 60, 60. And we're chopping in half. All right. Any ideas what a good side length might be for this? Again, it doesn't matter. You could pick pi, you could pick 10, you could pick 3, you could pick whatever. You'll get the same trig function values. But there's one number that actually is the most convenient. Any idea what that number may be? It's not 1. Because if we did put a 1 down here, then we have to chop it in half to get this triangle. This is kind of the triangle that we're targeting. So what do you think? Makes the most sense to pick an even number. 2 is the smallest even number. Any other even number would absolutely work because you're cutting it in half. But 2 is the smallest even. That's going to make the most sense, actually. So if we do a 2, 2, 2, that makes this a 2, and it makes this a 1. And now we have a right triangle with a couple of sides, the hypotenuse and the shortest leg. Then we just do some math, some Pythagorean Theorem to get the height. So we'll call it B. Let's call that height b. So we know that b squared plus 1 squared would have to equal 2 squared. So we know that b squared plus 1 is equal to 4. So b squared is equal to 3. Again, we're dealing with a length, so we don't need to deal with the negative square root. And there's b. That's how long side b is. That's the height of this triangle. Root 3. That's b. There it is. So now, let's focus on the 30-degree angle. Let's figure out what our trig function values are going to be for 30 degrees. First one is sine. Sine is opposite over hypotenuse. What is the side length that is opposite 30? 1. Hypotenuse is 2. So sine value is 1/2. What does that make the cosecant of 30 degrees? 2. Mm-hmm. All right, cosine of 30 degrees. So looking up there, cosine, the adjacent side is square root of 3. Hypotenuse is still 2, so we get root 3 over 2. Which makes the secant 2 over root 3, and if we rationalize that, we get 2 root 3 over 3. Okay. Tangent of 30 degrees. Opposite over adjacent, 1 over root 3. If we rationalize that, multiply numerator and denominator by root 3, we get root 3 over 3. So we did that from the triangle. We did opposite over adjacent. You could also do it from sine divided by cosine. 1/2 divided by square root of 3 over 2. Take the reciprocal of the denominator's fraction. The 2's will cancel. And you get 1 over root 3. Either way. Cotangent of 30. Which of these fractions is the better one to flip? The first one. Because then you don't have to deal with any rationalization. You're already good to go there. It's already rationalized. Denominator is already rationalized. Good. Now let's focus on 60. Sine of 60. Opposite over hypotenuse. So root 3 over 2. The reciprocal of sine is cosecant. That's 2 divided by root 3. We have to rationalize that denominator, so we get 2 root 3 over 3. How about cosine 60? I don't know anyone's name yet, so I can't. I guess I could point. 1/2. What's your name? Taylor. 1/2, and then the secant would be 2. Tangent 60? Square root 3? Square root 3? Everybody agree? Opposite over adjacent, root 3 over 1, that's root 3. Take the reciprocal, we get 1 over root 3. Rationalize that, we get root 3 over 3. Obvious connection between 30 and 60. If you look at sine of 30, cosine of 60, they're the same. If we look at cosine of 30 and sine of 60, they're the same. what type of angles are 30 and 60? 30 and 60 add up to 90 degrees, so what does that make them? Complementary. And the trig functions that we're dealing with here are sine and cosine. There's a word called cofunction, and that's what sine and cosine are. Sine and cosine are cofunctions. And in a couple slides, I'll have a summary of this. I just want to sort of point it out. So what we see is that if you do the cofunction of complements, you get equal value. Cofunctions of complements are equal. And that's coming in a slide. But foreshadowing. Tangent and cotangent are cofunctions. So if we look at these ones, tangent of 30, its cofunction is cotangent. The complement of 30 is 60, and we get equal value. So cofunctions of complements are equal. Might as well write that down right here. Even though it's coming on a slide soon. Cofunctions of complements are equal. All right, so why don't we take our 10-minute break, and then when you come back in, I'll do the roster, and we'll go from there. So come back 11:20. It's 11:10 right now. We'll start back up at 11:20. Take roll and do some more math. Let's resume. Unless there's any questions on triangles before we go on and talk a little bit about calculators. As you looked over your notes, anything not make sense? Feel good so far? All right, calculators. So that's the calculator I've got, 30x, just a little scientific calculator. That's all you really need for most of what we do. The one thing that gets a little tricky in the beginning is the conversion between degrees and degrees, minutes, seconds. And you know, there's two ways to look at a partial degree. You can use decimals and do a decimal degree number. So you could say something like 40 degrees and 30 minutes, or 40.5 degrees. Those are the same thing. Let me write that down just in case. So this is just different. So note that 40.5 degrees that's the same thing as 40 degrees and 30 minutes. There are 60 minutes in 1 degree. So in half a degree, there are 30 minutes. So those are the same. And in practice, you know, most everyday folks are just going to use decimal degrees. But there are some applications, navigation and things, where they will use a breakdown of a degree into minutes and seconds. I'm not going to do a ton of it, but you should be able to convert comfortably between the two. Whenever we do a conversion in math, we use a conversion factor. A conversion factor always has a value of 1. Because a conversion factor is shifting units. It's not changing value. Okay, so conversion factor should always have value of 1. And so we define 1 degree to be 60 minutes, and that leads us to 2 different conversion factors. We can divide both sides by 60 minutes or divide both sides by 1 degree. Doesn't matter. Either way, you will get a conversion factor. Conversion factor has value 1. So 60 minutes divided by 1 degree should have value 1, since 60 minutes and 1 degree are the same. You could also do the division the other way. 1 degree over 60 minutes is 1. So those are conversion factors. And you just have to choose the right one depending on what you're converting to, what you're trying to cancel out. Similarly, down here, 1 minute is defined to be 60 seconds. So you can do your conversion in either way. You can do 1 minute divided by 60 seconds. That has value 1. Or you could divide the other direction and get 60 seconds over a minute. That also has value 1. So those fractions can be used to convert. All right, so let's do this one right here. So we have 35 degrees. And you can bust this apart into terms. Plus 20 minutes plus 30 seconds. So that's a DMS angle, degree minute second angle, DMS. And if we want to change it to a DD angle, decimal degrees, we need to do a unit conversion so that the minutes become degrees and the seconds become degrees. We want to do a conversion. So we'll look up at our conversion factors. We want minutes to cancel out, and we want to be left with degrees. So should I use this first one or the second one up here? We want the minutes to go away, and we want to preserve degrees. Second one, because the degrees are in the numerator in that second one. So we're going to multiply this by this conversion factor. We have minutes in the numerator on the 20, minutes on the 60 in the denominator, so those units of minutes cancel, and we're left with units of degrees. 30 seconds, if we want to convert that, we want the seconds to go away, so we're going to use this first factor here, so we'll be left with minutes. So we're going to multiply by 1 minute is equal to 60 seconds. There, let's see, what should I use to do the cancellation? So those are going to cancel. Those are going to cancel. We aren't quite there yet. We still have to do one more multiplication. We're going to do 1 degree over 60 minutes. And then the last units cancel, and we're left with degrees. All right, so that's going to be our decimal degree number. And it's not always going to be easy to just add that up in your head. Typically, at this point, you're just going to type it in your calculator, unless it's super easier than you think. So here we have 35 plus 20 divided by 60, or 1/3, 1 divided by 3, plus 30 divided by 3600. If you want, you can say, hey, wait, a 10 will cancel with one of those. You can do that. You could also do the 30 goes into 60 twice, regardless, whatever you end up with. 1 divided by 120, something equivalent. All right, and you end up with 35 point, let's go to the nearest hundredth, 35.34 degrees. So that is our decimal degree equivalent, 35.34. So in other words, the 0.34 piece, that is, in this particular case, because we didn't bump the 35 up at all. Well, I guess we shouldn't if this was reduced. But that 20 minutes, 30 seconds, that's this decimal part right there. That's the 0.34. So 0.34, so 34/100ths of a degree is 20 minutes, 30 seconds. Let me give you one to do. Let's put in a slide here, and let's do one. So you guys convert this. So let's say 25 degrees, 45 minutes, and 23 seconds. So that's a DMS angle, and let's convert that over to a DD angle. So go ahead and start using your conversion factors. Should I put those up there? Or? So we have 60 minutes over 1 degree, 60 seconds over 1 minute. Or you could reciprocate them. So use whatever ones you need. raise a hand if you're totally confused, and I'll come help you. Oh. Thanks. You're welcome. Good luck. Trouble? Everyone doing okay? On the test, remember, you can't use a phone on the test, though. But if you have your calculator on there and you need to type it in real quick, that's fine. All right, so let's blow this out. We're going to think of this as 25 degrees plus 45 minutes plus 23 seconds. We need to toss in some conversion factors. We want the minutes to go away, so we want degrees on top. So we're going to do that. Similarly, over here, we want seconds in the denominator so that they cancel. Now we got to keep on doing that. Oops. And we end up with this. Does that look good to everybody? If you do this type of stuff, they usually call this in chemistry classes, what do they call it? Stoichiometry. Pardon? There's something that they use with you. What do they call it? Dimensional analysis. Yeah, dimensional analysis, where you try to get all these units and get them all canceling and you end up with what you want. Dimensional analysis, that's what they call it. They always complain to the math teachers that the students can't do dimensional analysis. What are you teaching them? Teaching them real math. All right, so then type all this stuff in. And we end up with 25 plus a fraction of a degree. And if we round to the nearest hundredth, that would be 0.76 for the end. So that's our decimal degree number. Now, it is the 21st century. And most of us have calculators. We had to use our calculator anyway, unless these were really super slick fractions that canceled so nicely. We had to use our calculator anyway, and if you notice up here, every calculator these days has a DD to DMS or vice versa conversion. So you can also use your calculator directly. So if you're going to use your calculator anyway, it's not a bad idea to just know how to do it with the built-in app that converts. And so that button right there is the degree minute second button. And so if I wanted to enter this using this calculator, and most of them are pretty similar, I would type 35, and then I need that degree symbol. So if I click that menu, you're going to see that you can use the left and right arrow keys to get to degrees, minutes, and seconds as units. So I'm choosing the degree symbol, and then I'm going to type in 20, go back to that same menu, slide over, choose the minutes, and then type in 30, go back to that menu, slide over to seconds, and then if I press enter, it automatically converts it 35.34 to decimal degrees. So automatically will do it. And you can go backwards just as easily, although I'm not seeing the key off the top of my head. I thought it was right there. Oh, there it is. So on that same menu, if you've got one of these little $10 calculators, if you keep sliding to the right, it's on the next screen. You slide past, it goes degrees, minutes, seconds, and then some things you probably don't want to know about, 2 things, and then it hits DMS. And so if I just go all the way over to DMS, it converts it back to DMS, 35, 20, 30. So that's a convenient little way to do it also. All right, let's go backwards now. Let's do DMS, or generate a DMS representation of an angle that's given to us in decimal degrees. So here, we're starting with 84.35. I'm going to think of this as follows. So I'm going to write that 0.35 as 35/100ths. And we're going to use a conversion factor. If we want to get to DMS, we want those degrees to go away. So we're going to do that first. Bless you. And if we type this into our calculator, 84 plus 35 times 60 over 100. You can cancel a 0 if you want, or whatever your preferred arithmetic process is. And we get 105. Oh, we're done. 100. Wait a minute. Something's wrong. I divided wrong, I think. I think I divided wrong. Type it in again. 84 plus 35 times 60 divided by 100. I think I only divided by 10. No, I'm getting 105?
That's what I got too.
What the heck? Oh, my bad. We can't combine these. These are not the same anymore. Right? One is degrees and one is minutes. This is 84 degrees plus, right, our units here are now minutes. So we got to do 35 times 60 divided by 100, and that's minutes. So that's 21 minutes. That's the mistake. And so that gives us our DMS answer. There's no seconds in this case. It gives us that. So the units over here are, we're canceling out our degrees, so the units here are minutes. So 35 times 60 divided by 100 gives 21 minutes. Do one more of those. Give you guys one to try. All right, you ready? Put another one up here. Bless you. All right, so there's a decimal degree number, and let's do a conversion to DMS. So do that using your conversion factors. Let me know if you're hung up on anything. As we're moving through the semester and I'm writing stuff on the board and talking, you see that I've made an arithmetic mistake, make sure you point it out. Don't just bite your tongue. It's very easy when talking and writing at the same time to have a typo. Yeah. Do the whole thing start to finish. So on this one, remember, they're all just a little bit different. And you see something where it says angle right there. Oh, okay, yeah, so it's not all the way down. Gotcha. Yeah, if you're poking around in your calculator and you're not sure exactly where the DMS to DD conversion is or vice versa, let me know and I can figure it out. Dr. Google can also help you. All right, so the way we would convert this, we're going to think of this as 150 degrees plus 62 1/100ths of a degree. And we need to ditch the degree symbol there. So we're going to use a conversion factor. We're going to multiply, let's see, we want the degrees to go away. So we want the 1 degree in the denominator so the degrees go away. We have 60 minutes in the numerator. And we're going to have to type that into our calculator, remembering that those are not like terms anymore. The first one is 150 degrees. The second one is minutes. So we'll do 62 times 6 divided by 10. 37.2 minutes. Oops, we've got a fraction of a minute. So then we do the same type of thing. We're going to come down here. We have 150 degrees plus 37 minutes plus 2/10 of a minute. We're going to convert that over to seconds. We want the minutes to cancel. So we're going to do 60 seconds is 1 minute. And that we don't really need to type into our calculator. We can manage on our own, I think. So that's 150 degrees, 37 minutes. And then the seconds will have 120 divided by 10. So that's 12. So that would be our DMS representation of that angle. Pretty good? Not too bad. Not too bad. Doesn't feel like we're doing math, though. It feels like we're doing something else. It feels like we're doing arithmetic. All right. Let's get back to math. There's our abstractness that we're pining for. All right, so I mentioned this before. We talked a little bit about this concept that cofunctions of complements are equal. Cofunctions of complements are equal. And this summarizes that. If we think about a right triangle, and we identify one of the acute angles as theta, the other angle is necessarily its complement, the other non-right angle, the other acute angle. Everyone agree with that? We know that the angles in a triangle add up to 180. This angle here is 90. So those two have to add up to 90. So that one down there has got to be the complement of that one. And the complement of theta is 90 minus theta, if we're in degrees. So let's just confirm that this is true. Let's use some letters. Let's call this side A. Let's call this side B. Let's call this side C. Well, let's just notice. If we find the sine of theta, sine by definition is Sol.
Yep.
Sine is opposite over adjacent? No. Opposite over hypotenuse?
Yeah.
B over C? Everybody agree? We agree? Are we all on the same page? Okay. Now, let's look at the cofunction of sine. What's the cofunction of sine? Cosine. And what's the complement of theta? 90 minus theta. Right? So let's go to that angle. Cosine of that angle is adjacent over hypotenuse, and that's B over C. And that's what we would expect. So that checks. Right? We found sine of theta, and then we took the cofunction of the complement and got the same value. Cofunction of complement, same. Make sense? Let's confirm at least one more of them. For grins, let's go ahead with tangent. Tangent of theta is... What would tangent of theta be with sides A, B, C? B over A. Opposite over adjacent, so B over A. And what is the cofunction of tangent? Pardon? Sine over cosine is the reciprocal identity for tangent, sine over cosine. So cofunctions, we have sine and cosine.
Tangent of 90 minus theta?
Yeah. So tangent and cotangent are cofunctions. So we get cotangent, and the complement of theta is 90 minus theta. Right. So both those are B over A. Double check when you go look at 90 minus theta, cotangent is adjacent over opposite, which is B over A. Might as well write the third. Oh no, let's do. Yeah, let's write the third one down just to be complete. So we started with sine up there. We started with tangent there. Let's start with cosine. And this one's very similar to the one up there. The cofunction for cosine is. Oh, before we get to that though, let's just find cosine of theta with our picture. Cosine of theta adjacent over hypotenuse, A over C. And now the cofunction of cosine, sine. The complement of theta is 90 minus theta. So we get that. When we look at our picture, if we were to take sine of 90 minus theta, sine of that is opposite over hypotenuse. It's A over C. So both are the same. Cofunctions of complements are equal. So let's look at a specific example. Thought that there was a specific example there. I will get one. Let's go get one. So, let's take a look at, I had inserted it. I must have not saved it. But easy enough. We have the power. We can get as many examples as we want. Study plan 6.1. So right now we're focusing on the trig functions of acute angles, and very soon we're going to generalize that to finding trigonometric function values for non-acute angles. So what we're going to do, and this happens a lot in math, you make definitions for a certain set of angles or some restricted group, and then you extend that, you generalize that. And so that is what we will do shortly, like in the coming days. We will get my capture tool up and running. Let's go back to here. Okay, we'll do this one. Turn down the volume of that shutter. That's enough, I guess. I don't know what negative 8 means. Okay, so we want to rewrite 59 degrees in terms of a 31 degree angle and in terms of the reciprocal of a trigonometric function. So first off, we notice that there's a relationship between 59 and 31. So clear that 59 and 31 are complements. They're complementary angles. And so what we can say, and all they're wanting us to do here is sine of 59 is the same as the cofunction of the complement. So cosine is what's going to go in there. Not too bad. Let's pick another one. I wanted to get one that's a little more complicated. Let's go back here. What I was looking for was that one. That's what I wanted. Okay, so here we have information about an angle, 62 degrees. We are given the decimal value of sine of all these things up here, of 62 degrees. And it's asking us to figure out function values for the complement of 62. So once again, we're in this position where it's pretty contrived. You know, we've got that 62 and 28. Those are complementary. And so what we can do is find the values that they want us to find by using the values above. And I'm going to write it over here. So sine of 28 degrees. That should be equal to, what's the cofunction for sine? Cosine, the complement of 28. 62. All right, so then let's go up here and look. So sine of 28 is the same as the cosine of 62. Come up here, cosine 62 is 0.4695. So that is the trigonometric value for sine of 28. So that's what they're trying to get us to comprehend. Cosine 28 degrees. Cofunction of cosine, sine 62. Look up there, we get 88.29. That'll be our value. And then the last one, tangent of 28, will be cotangent of 62. And that is 0.5317. How's that look to everybody? Is that okay? Ask if you are confused at all or if you want any clarification. All right, so now what I want to do is I want to do a couple. I want to talk a little bit about some stuff in 6.2. We'll get into greater detail on Thursday. I want to do a couple of applications. In particular, I want to do one that reminds us of college algebra. So this is on page 507. Do you remember how we solved systems in college algebra? Yeah. All right, we'll do it again today. Does anyone know what a system is? 2 equations, 2 unknowns, 3 equations, 3 unknowns, 4 equations, 4 unknowns. What were the 2 techniques you learned if you had a system, if you had 2 equations with 2 unknowns?
Substitution.
Substitution is one of them, absolutely. And then the other one was?
Elimination.
Elimination. Genius. We're flying. All right. Let's close that. And got to get into the book for 6.2. I want the exercises for 6.2, which are at the end of 6.2, maybe closer to the beginning of 6.3. We're going to look at this one application I like to refer to this type of problem as the nasty algebra problem. And it will be a system that we solve, and it will be on the test. So you've got to figure out how to keep it all straight. So it's this problem. Yeah, right. You have to go back one more slide. I think it's on other side. And the idea here is that we want to figure out how high the Golden Gate Bridge is, given some information.
What page is this on?
507. 507, 6-2. A little bit of a refresher before we get into 6-2 in earnest. Page 507. All right. So, Golden Gate Bridge got towers, equal height, turbo, blah, 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 blah. So, let's look at the math. So, the estimate is that the angle of elevation is 30 degrees. Maybe I should mention real quick. Angle of elevation. When we talk about, there's two types of angles that they often give us measures of. Angle of elevation and angle of depression. Angle of elevation and angle of depression are both from horizontal. Angle of elevation just means the angle from the horizontal up, elevation. Angle of depression is from the horizontal down, angle of depression. So angle of elevation, angle of depression, nothing more than the angle between the horizontal and whatever we're looking at. So here, there's a measure of 30 degrees between the horizontal and the top of the bridge. And then they tell us that the sailboat sails 650 feet closer. And this is a totally contrived problem. Who's measuring how many feet their sailboat is sailing? In practice, this type of thing is used in surveying, but typically, you're walking on land and you can walk, 50 feet, and your tools can tell you're walking 50 feet. On water, this is definitely contrived. But the idea is that we take a reading out here, angle to the top is 30 degrees, we come a little closer, angle to the top is 50 degrees, and we should be able to use those two data points to figure out how tall that tower is. So what we do, we're going to take a look at both right triangles that we see. We see this right triangle in here, the inner right triangle. And then we also see the outer right triangle there. And my yellow and green are combining, but maybe I should write the green one outside of that. Okay, so we have those two nested triangles, the yellow triangle and the green triangle. Each one of those triangles is a right triangle. We're going to generate an equation for each. Let's see what happens. So when we're looking at the inner right triangle, I see that 50 degrees is right there. And if I use the tangent function, I don't have a measure for this right there. Don't know what that is. You agree? Don't know what it is. So what I'm going to call it is whatever I want to call it. We've already used an x. They're using x for the height. Let's just call it y. Why not? X and y. You can call it whatever you want to call it. It feels funny putting y on the horizontal and x on the vertical, but they started it, not me. And that yellow triangle, if we use the tangent function, we have tangent of 50 degrees is equal to x divided by y. So there's one equation with two unknowns. Next, we look over here to the green triangle, and if we take the tangent of 30 degrees, similar type of thing, we'll do opposite over adjacent. So that's going to be opposite, which is x. And the adjacent is going to be this whole thing. So 670 plus y. So we now have two equations, two unknowns, and our goal is to solve for x. And we have two choices. We could eliminate y and solve for x directly, or we could eliminate x, find y, then back substitute and get x. A couple of ways to do it. And they're all totally fine. First thing I want to do is just get rid of the fractions. Let's just clear out these fractions. So this first equation, I'll write it as x equals y times the tangent of 50 degrees. Clearing out the fraction there. And then the second equation in this system, the second equation is, we want to clear that fraction. Tell me if this is not crystal clear. The second equation will be 670 tangent 30 plus y tangent 30 equals x. Does everybody see that? To clear the fraction, we have to multiply both sides by 670 plus y. When you multiply the left by 670 plus y, the denominator and that factor just cancel. But when you multiply this side by 670 plus y, you've got to do some distribution. That tangent of 30 needs to distribute to each of the terms inside the set of parentheses. Okay, so we have two choices now. Two equations, two unknowns. Looks really easy to set these equal to each other and solve for y. The problem didn't ask for y, though. But you could easily get x once you have y. Totally legitimate way to go. That will work. You can also, if you want, try to rewrite this so that it's directly going to solve for x instead of directly solving for y. Again, it doesn't matter. It's your choice. I am going to rewrite this as y equals x over tangent 50. The only reason I'm going to do that is then I'll just plug it in right here, and I'm solving for x. Because that's what we want to solve for in the end. Doesn't matter, though, if you're more comfortable solving for y first and then back substituting, totally fine. There's lots of ways to solve systems of equations. So the choice I made was to plug that in right here. So I'm going to have that fraction substituted in, x over tan 50. That's multiplied by tan 30. That's all equal to x. Okay. Now here's an equation. I claim you can solve this easily. If you had this equation over here, let's suppose we had 5 plus x equals pi x, something like that. First off, how do we classify that equation? Is it linear or non-linear, that equation? Five plus x equals pi x. Linear or non-linear? Those are the most important two classifications in college algebra. You need to know if you're dealing with a linear equation, you solve it one way. If you have a non-linear equation, you solve it another way. Two different techniques that you guys learned. But before you know which technique to use, you have to be able to identify it easily. Is it linear or non-linear? It's linear. We look at the exponent on the variable. Exponent is 1 on both iterations of x, so it's linear. And we know that with a linear equation, all the x's go to the left. All the terms that are constant go to the right. You get a coefficient, you divide it to the other side. For nonlinear, everything goes to one side. The other side becomes 0, and you factor. Nonlinear equation, everything to one side, 0 on the other, and factor. Linear equation, all the x's to one side, all the constants to the other, and then you divide. So let's finish this one off. So if I follow that principle, I would have x minus pi x equals -5. if I move the pi x to the left and the 5 to the right, I have x minus pi x equals negative 5. Then what would we do? Factor out the x. If we have x appearing in two places, the way we isolate x would be to factor it to the front. So we would have x multiplied by the factor 1 minus pi equals negative 5. And then the final step to isolate x, divide by that coefficient. And we would have negative 5 divided by 1 minus pi. So that's all we're doing. That's what this is. That equation that we're looking at on the board is a linear equation with a lot of extra stuff. But that extra stuff, constants. Those are just constants. Tangent of 30, constant. Tangent of 50, constant. 670, constant. So that is linear. So we need to identify that this is a linear equation. And for a linear equation, x is to one side, constants to the other. This is a constant. That's a linear term. So I'm going to leave the 670 tangent of 30 alone. Just leave it on the left. And on the right, I'm going to do x minus. And let's see if I can combine this a little bit. This is tangent of 30 over 1. So I can think of this as tan 30 over tan 50. I can think of that as the coefficient of x. That's it. Next step. X is appearing in two places on the right side. We need to consolidate so that there's only one x. To create 1 from 2, we did it over there. What do we do? Factor, right? Factor out the x. Exactly. So we're going to factor out the x. And then the last step, or maybe it's not the last step, what do we do next? The next step? The last step is going to be typing it all into our calculator and not making a mistake, typing it all in. But the next step, how do we isolate the x? Divide it out. Divide out that big nasty coefficient. So this tells us that x is equal to the following. 670 multiplied by tangent of 30, all divided by this. And this is our final task is to make sure you are capable on your handheld device to type that in and not blow it. When you're entering something like that, the first thing that you notice is that the denominator has two terms. Those terms have to be wrapped in parentheses. Right? When you do the division on your calculator, that's got to be wrapped up. So you're going to type in the numerator. The numerator is just one term, so that's no big deal. 670 tan 30. But one thing that you may or may not already know is that your calculator has a degree mode and a radian mode. When you get into calculus, angles are usually measured in radians instead of degrees. It's just another way to measure an angle. So make sure your calculator is in degree mode because we're using degrees. We're measuring our angles with degrees right now. We'll talk about radians in the near future. There's a really good reason to use radians instead of degrees when you're doing calculus. Now, when I type this in, I'm typing tangent 30 for this numerator. You have to be careful because the calculator is automatically putting a left parenthesis. We need to close that off by putting the right parenthesis around the 30. So tangent of 30, wrap the angle. So in your calculator, you should be seeing, on most of them, it depends on the calculator, but that's going to have to be wrapped up, that's going to have to be wrapped up, that's going to have to be wrapped up. And then we type the division symbol, tangent 50. Wrap the 50 and wrap the denominator. There should be 2 parentheses. And then equals, and I'm getting 750.32. And then we look at the problem and figure out what the units are. Did we round to the right place? Does the answer seem logical? You know, if this answer was negative or something, which when you're typing in all this stuff, if you forget a set of parentheses, you could easily end up with an answer that's negative instead of positive or whatever. You just want to look and make sure that it seems reasonable. So it says approximate the height of the tower to the nearest foot. Okay, so we'll round that. This was 670 feet. So, you know, as long as they drew this picture proportionally, yeah, that answer seems reasonable, 700 something. So to the nearest foot, 750 feet. That would be our final answer. So practice that. There definitely will be some heartburn with that algebra as you play with it. But that type of algebra problem will be on the first test. So you practice it enough so you can do it efficiently and quickly enough. And you're not spending 2 pages trying to figure out it's just a linear system. It's just that there's a whole bunch of extra decorations. But all that extra decoration is just constants. And that's what I recommend a lot in this class, and in particular as you're going into calculus. You want to have some of the bigger concepts down in your head. If you have a linear equation, know what the procedure is to solve. If it's nonlinear, know what the procedure is. And it's not always identified in algebra as that precise, but those are the 2 types of equations you deal with. Nonlinear, one-side factor. Linear, separate the variables. Separate the variable and the constants. All right, let's stop there. We will meet back here in 48 hours, minus 2 hours and 15 minutes. And over there at 9 o'clock on Thursday, Jess will do some study sessioning. Welcome to Fall 16.